computer. Okay. Greetings, Earth and space explorers, and happy solstice worldwide. Welcome to Doc Waller's Earth and Space Report for Friday, December 22, 2023. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cold, moonlit evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on Cape Ann's community access cable television channel hosted by 1623 Studios. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists, educators, and communicators around the world, far-flung friends, family, and other curious folk. Thank you for your active participation, comments, and general encouragements. For this 44th episode, we have Dr. Scott Acton coming to us from Colorado, who will present reflections on the Webb Telescope and cycling the world. Scott Acton grew up in the small rural town of Riverton, Wyoming. He spent several of his post-high school summers working in the uranium and petroleum industries, but soon began a series of internships at the Lockheed Palo Alto Research Labs, where he would eventually sign on as a full-time employee. While at Lockheed, Scott developed an adaptive optics system for use in solar astronomy. His work was the first unclassified demonstration of real-time atmospheric correction for high-resolution imaging. Scott earned a PhD in physics from Texas Tech University in 1989. He later spent a year as a postdoc at the Kiepenheuer Institute for Sonnenphysik in Freiburg, Germany. Following his postdoc, Scott became the adaptive optics engineer at the W.M. Keck Observatory in Hawaii, building and commissioning AO systems for both of the Keck telescopes. Scott has worked on the James Webb Space Telescope since 1998, joining Ball Aerospace in 2001. He was the wavefront sensing and control scientist for the project, leading the team that aligned the telescope optics after launch. In April of 2016, Scott took a one-year leave of absence from JWST and bicycled 10,000 miles across the United States and 10 other countries to promote this amazing telescope, a trip he hopes to repeat one day. There's lots to discuss here, so Scott, the Zoom platform is all yours.
All right, well, thank you so much. Let's see if I can get my screen shared and get it going. And okay, well, oh, wrong one. Hold on, I did same mistake. Hold on 1 second. Screen share. I want to share this screen. Share. Now come over to here and start the presentation. All right.
Okay.
Everybody see a picture of a spacecraft?
Bingo.
Excellent. So this is I call this farewell Webb. It's the last the last picture of the telescope taking as it was moving away from the Earth. There's the Arabian Peninsula down there, and it was a complete accident. They just were simply interested in whether or not the upper stage disconnected. But what a beautiful, beautiful image to say goodbye to an old friend that we've known for 20 years. After this launch, this is when my role on the project began, or at least in earnest. And that I led a team of people that basically did all of the wavefront sensing and control. So we did all the algorithms initially the first few months to put all the mirrors in the right place, so that instead of just getting a blob of light, we ended up getting a diffraction limited image. Now I'm going to show you a lot of pictures of the telescope. And here's one, for example. All right, that was recently taken. Just beautiful, beautiful images. Here's one, the very first one that was released by President Biden, and as sort of a little teaser for the public. But a lot of the pictures, here's another one. This is the Stevens Quintet. But a lot of the pictures I would show normally look like this. they're kind of horrible, right? But it's got to look like this before it can look like that. And so, in this particular presentation, I've got a section where we'll talk about how we step through that whole process and all that, but I'm going to show a sort of movie. I have an entirely different presentation where it's just about that, about the science of wavefront sensing and control. Now, I do want to show, I'm going to show a lot of scientific results, or some of them, but one in particular that has me really excited. And I don't know why the media and everything isn't just going nuts over this. But recently, a couple of months ago, there was a conference where someone presented a differential spectra of the planet K218b, which is a star. The star is about 120 light years from here, and there's a planet that is orbiting around that in a very close orbit, but it's a cool dwarf, so that that planet is actually in the habitable zone. And we knew there was water on that planet from differential spectra taken on Hubble. But now we know that there's methane, carbon dioxide, and, wait for it, dimethyl sulfide. And on Earth, the only place we know how to make dimethyl sulfide is associated with actual life, microbial life. And of course, we can't prove it. This is a step in that direction. But you may be looking at the first discovery of life outside of the Earth. And I emphasize the word may. And nobody wants to be that one that jumps the gun and makes some big announcement that proves to be true, but not true. But so anyhow, I'm very excited about this scientific result. And it all started in 1996 when the Dan Golden, the NASA administrator, kind of challenged people to stop thinking so small and to start talking about building a really large telescope. And that was the beginning of the Webb telescope. Here is a picture of it nearly completed. You can see it says a segmented primary mirror, and it's got a sun shield that's all folded up just before we're getting ready to ship it to the launch site. And here's a model of what one looks like, the telescope looks like when it's deployed. It's enormous. This telescope is really, really big. And that sun shield there is the size of a tennis court. This is taken out, this is just a model, but it was set up in front of an old church in Dublin, Ireland. I was there at a conference, and I'm there in the back row. And the church is an old Catholic church that was converted into a museum, and I'll show a picture from the inside of that later on in the presentation. But so I do want to take a little bit of break here and just talk briefly about why I did this. And so I found myself in kind of a perfect storm of circumstances. I was 55 years old, and my body hadn't quite figured it out yet. And my kids were out of the house. They were in college and all that. I could sort of afford it. And most importantly, the project didn't really need me for a little over a year. So I decided to form the James Webb Space Telescope World Bicycle Tour. The goal, ride my bike around the world, stop and give talks to promote the telescope and all that. And there's my bicycle, and there's sort of the route that I wanted to follow and all that. And it was neat. I got here's the patch, I got sponsors, got a website. It's still there if you want to read about the blog and the experience and all that. Got jerseys. I got people to go with me on the ride. And I also got this little pain in my chest whenever I'd get on my morning. We get out in the morning on the bicycle. Now, normally I would have ignored it, but I figured with a big ride like this coming up, I better go to a doctor. Well, one thing led to another. One test led to another, one doctor led to another, and come to find out the arteries in my heart were clogged beyond the world's wildest imagination. I was dazed from death and had no idea. The doctor said, my daughter was getting married in 3 days, so I asked him if I could wait a few days for the surgery, and he said, yeah, that'll work. That way all your family will be in town for the funeral. And so I didn't. I attended the wedding by FaceTime, on a telephone from the hospital. But I point this out. I know this isn't what you come to see here today, but whenever I give a talk, I talk about this. Guys, I want you to know that this surgery is optional. You don't have to have it. The science behind your blood chemistry and your risk for heart disease is 100%. You can take a blood test that will tell you your future. And I would encourage you to just, you're all intelligent, to go out there and get yourself checked and see where you stand in terms of your risk. And maybe you can change your lifestyle and not have to have a surgeon take a circular saw and cut your chest open. All right. But in any case, I did it. I never had a heart attack. So the recovery was very, very good. And I got on the bike and I went ahead and started the ride several months later. But let me ask you this question rhetorically, since we're all muted on Zoom here. But I always ask this to kids when I give a talk, say, where is the center of the universe? And invariably someone will say, yeah, right there, right in your own town. And I say, okay, well, imagine we live in a three-dimensional world. Imagine we only lived in a one-dimensional world. You got this, there's no up and down, no left and right, just forward and backwards. It goes on infinity in each direction. Where's the middle? Well, they all agree that there is no middle. Okay, but what if I take this one-dimensional universe and I bend it because of the presence of gravity? I bend it now that it's in a circle. Now they don't know it's a circle, okay, but they still live in that little one-dimensional surface. So where's the center of the universe now? Well, it's obvious. It's in the middle of that circle. Can they get there? No, they can't. But it doesn't mean it doesn't exist. Okay, well, it comes down to basically, if you want to talk about the center of the universe, you have to introduce another dimension. And that dimension, in this case, is time. So the center of the universe is everywhere 13.7 billion years ago. All right, so if something happens, say 13 billion years ago, back to the one-dimensional example here, some event occurs and light starts traveling through space. It goes on and on and on, and eventually it hits our telescope. Right there, I take a picture of it. I'm not looking at that thing in the past. I'm looking at that thing that happened 13 billion years ago. So when we look at something through a telescope, we're not just looking at a long ways away. We're looking backwards in time. So we can study what the universe was, a long time ago, which is what makes it really exciting. And so we talk about this thing, and now maybe I make a two-dimensional example where I've stretched out the sky to form a two-dimensional plane, and I've stacked those so that we can kind of see them, how they progress through this other dimension of time right here. And so when we had the Hubble telescope, it allowed us to look backwards in time to some extent, and to be able to get the occasional gravitationally lensed galaxy. The ground-based telescopes were a little, not quite as effective, but the the Webb telescope is allowing us to look almost right back to the very beginning, back to the first light. All right. So the challenge is this: we want to see some things that are very, very small because they're so far away. They're very faint for the very same reason, and they're red because the universe is expanding, and we have this this red shift due to the expansion of the universe. And in some cases, we're wanting to see through various dust, so that we can see things. And that can be a problem, particularly when you're looking at stuff in our own galaxy. Well, if it's very small, we need to have a big telescope if we want to see it. Very faint, we need to have a big telescope in space so we can get away from the scattered light. And because we want to see that it's very red, and we need to look into the infrared wavelengths, we need infrared instrumentation, and the telescope has to be very, very cold. Now, that's something people don't appreciate, that if we're looking at the infrared through a telescope that's at room temperature, what we're going to see primarily will be thermal emission from the telescope and not from the object we're looking at. So anyway, the answer to this, of course, is the James Webb Space Telescope. It satisfies all these things here. Now, I want to give you an example. Here's a picture of a man whose arm is under a garbage bag, looking at it in invisible light. You don't see through that, but when you switch to the infrared, you can see through that material. The same thing has to do with when we're looking through dust clouds in our own galaxy. Like we've all seen this picture of the Eagle Nebula, a Hubble image. All right. But look what happens when you shift to the infrared. You see all those things, and those just aren't background stars. Those are stars that are actually in the nebula, and we don't see that. There's all sorts of star-forming regions and everything that you can see that you can't see if you're looking in the visible. So infrared is the tool that allows us to look somewhere that we've never looked before. And of course, the instrument itself is the James Webb Space Telescope. Here's some pictures of it as it was nearing its completion. I believe this is out of Northrop Grumman. We're the prime contractor on it. Here's another picture. There's members of my team anyway, or the people that I worked with, standing in front of the telescope. And if you look very carefully, you notice one of the mirrors is tilted off a little bit. I'm probably the only one in the world that noticed that, but for whatever reason, that thing was tilted at an angle. Now, the telescope itself, it had a very, very lightweight design. It has, a deployable set of mirrors and a secondary mirror. And it had the backplane that held everything together. It was made out of a lightweighted graphite, a composite, epoxy composite. It was specially formulated for work in the cold. It had these thermal management systems, these radiators on the back, and of course, all the science instrumentation. The telescope itself was attached to this tower that would deploy and move it away from the rest of the spacecraft after launch. Okay. Now, this is a picture I show people if they ever want to know a good definition of narcissism. Narcissism is taking a picture of yourself in a $10 billion mirror. And I was just up there one day and a NASA photographer said, "Hey, stand right here. I'm going to take your picture." And boy, what a souvenir to take from working on this project, huh? All right. So anyway, we don't have to show that anymore, but it's I enjoy this. Here's some of the other optics that are in there. On the left, you can see a primary mirror segment, the secondary mirror, and this telescope is a little different. It actually has 4 mirrors. It has a third powered mirror. We call that the tertiary mirror. And then it has a 4th mirror, which is just flat, a fold mirror. But that is located very almost right out of pupil of the primary, an image of the primary mirror, so that if you move that around, you can control the stability of the image. You can take out telescope vibrations and line of sight jitter by controlling that 4th optic. All right. Now here's what the mirrors themselves look like. On the back, they're actually mechanical devices. Each mirror has 7 actuators on the back, 6 to move it in a rigid body sense, and a 7th actuator to change the radius or curvature of that mirror. And it wasn't necessary to do that dynamically, but it helped us buy down risk. It turns out it's kind of hard to make individual mirrors that have the same radius or curvature. So this allowed us to adjust that value after the fact a little bit. All right. Now here's where they were manufactured. It was made out of the whole telescope started out as ore in these mines in Utah, where they mined the beryllium ore to make beryllium powder. And then the Brush Wellman took that powder and they would melt it down under extremely high pressures and temperatures, and they would make these blanks, which then got cut in half and then roughly machined, and then they would be sent to Axis Technology, and where they did the rough light weighting of the mirrors, and they would get rid of 92% of the beryllium and just get these down so that there's something that a person can easily lift 1 or 2 mirrors. So it's a very, very thin, but extremely strong and stiff because it's made out of beryllium. And finally, Tinsley Labs did all the polishing. But this was an iterative process with Tinsley Labs and testing and getting the right figure on everything. So it turns out that we had to go back and forth between these, and I have a chart in a second that shows how that was done. But I want to deviate here just a little bit and talk about the ride. This was the first section of the bike ride where I left Boulder, Colorado on April 1st. And this was 6 months after heart surgery, and biked up. My goal was Dead Horse, Alaska. I didn't quite make it because the roads were just not navigable on the bicycle that I had, but I made it up through Fairbanks. And there was the first day. Went over the Continental Divide up through Wyoming. Terrible winds, boy. Terrible students. I mean, the most terrifying thing is to try to talk to 300 5th grade kids. But they were extremely enthusiastic, which was nice. Eventually, I went to the University of Wyoming and gave a talk there. Up through Thermopolis, Wyoming, a beautiful place if you've never been. It's the world's largest mineral hot springs. I don't know why they made a cake. Somebody did, but finally into Montana. And oh boy, I about died on Bozeman Pass. But the weather improved and the sun came out and things were good. And I enjoyed that section of the ride. I wanted to talk about where the telescope is currently. It's at a place called L2, which is about 1 million miles away from the Earth. It's kind of at a gravitational loophole that allows it to stay more or less with minimal intervention at a single point in space. So you want it to be away from the Earth and the Moon because you don't want all that scattered light and stuff, but you don't want it to get lost. You got to know where it is. So it's out there at L2, and that's about 1 million miles away. But I maintained that the telescope traveled 1 million miles before it ever went into space, and that had to do with fabricating these mirrors, because we had to go back and forth between integrating these mirror segments and testing them and polishing them and testing them in a cryogenic environment and on and on and on. And they had special trucks that moved these around. It was a special team that was the experts at transporting these mirror segments, a husband and wife team, and each segment traveled about 25,000 miles, and I figure 18 segment, that gives us 440,000 miles total. We'll call it 1 million, rounds up to 1 million. But here's the shipping containers. Each mirror had its own special environmental controlled shipping container. and they kept a positive pressure on it, and there's dry nitrogen and everything, and special trucks that wouldn't jar the mechanisms any much, unnecessarily. And but when I saw this picture, I don't know what you guys thought. I thought about that movie Alien. I don't know if you've ever seen that. Let's see, where are we at here? Oops, wrong way. I'm going the wrong direction here. Right, with all those little eggs, those little pod things where those things would come out and eat you and all that. I'm a real nut for science fiction, and that's kind of what came into my mind when I saw it. But science fiction is sort of the right way to describe this project. I mean, there's so much of this technology, it's science fiction, but it's real science fiction. It's science nonfiction, I guess. There's a picture of 6 mirrors being tested at the XRCF facility in Huntsville, Alabama. That's a cryogenic test facility. Now, I got to show you this picture here. This is my buddy, Matt Lalo. And you probably wonder why I would have a car in this thing. Well, Matt is, by the way, he's worked at Space Telescope for years. He was there from the very beginning of the Hubble mission. He's the telescope lead at that place. Matt has no children. Has recently got married, but he has no children. And in other words, he's rich. Okay. So he says, Scott, you invest in your children. I have none. And so I invest in really fancy sports cars. And so the Alfa Romeo 4C, if you look very carefully at this thing, that doesn't have a metal chassis. It's a carbon fiber chassis. And it's unbelievably light and strong, but that's exactly the same stuff that the backplane of this telescope is made out of, this graphite epoxy composites, specially formulated for cryogenic environments. Here's another picture of it. So it's very, very strong, very light. Here's a picture of the sun shield. Now this folded up and then unfolded itself after launch, but there's 7 layers to this, and it does this so that it keeps the sun off of the telescope. No light from the Earth or the moon or the sun can hit the telescope because it has to passively cool to 40 degrees Kelvin. And without this, that would never happen. So this is it. It's made out of aluminized Kevlar. It's extremely light, and nothing like this was ever done before. But the idea of folding this up and having it unfold without getting tangled was quite an engineering feat that Northrop Grumman solved. Here's another picture of it. Here's a picture of the telescope itself with the sun shield folded up in front of it. Right. Now, the science instrumentation is interesting because there are 7 different science instruments, and they each see a different part of the sky. So if you take a picture on one instrument and you want to see the same thing on a different one, well, you got to point the telescope slightly to a different place, right? So this is the near-infrared spectrograph. These are 2 redundant near-infrared camera modules. So they have completely redundant optics, everything, electronics, detectors, because we need those to align the telescope. And this is as a way to, in case one fails, we would still be able to get the telescope control done. This is the mid-infrared imager. And this is the near-infrared imager and the spectrograph. That's a Canadian instrument. And then these are the fine guidance sensors, also made by the Canadian team. Now, the fine guidance sensors they're imagers, but they're not really designed for science. They're designed so that we can find a star and guide on that star to take out all the vibration and jitter in the telescope during the integration as you're taking the image, right? And so, by the way, I should mention that this project was a combination between NASA, the European Space Agency, and the Canadian Space Agency. And speaking of Canada, so this is as I crossed along the border into Canada, and on the bike ride, and there I was in Alberta, and this was one of the roads that Google Map wanted me to put on there. What a beautiful place! Such a beautiful place in here. Just imagine, if you will, taking a ride in the mountains somewhere in the United States, or like I live next to the Rockies. So you get in your car, you're going through the Rockies, and just imagine that beautiful mountain vista continuing for 2,500 miles. That's what this was like. There I am on my bike. It just went on and on and on. Just so much but it's an unforgiving place. Very unforgiving, but just fascinating. You know, here it is the Sign Forest and Watson Lake. You know, just endless beauty. There are people there, but if you step just 50 feet off of the road, there's nothing. There's wilderness. Every river you see is loaded with fish. There are wild animals and strawberries and things everywhere. But just a beautiful place to go. I would love to go back. Here's my tent. Yep. There was the head of the Canadian Astronomical Society. I always managed to find myself a bottle of beer somewhere. This was the northernmost microbrewery. And then, boy, then the bugs came. Oh my goodness. We won't talk about the bugs. Then I came to a fork in the road and I took it. Yep, I took it. Then finally into Alaska. Now, in the project, as we completed the telescope, the time came to move it to Johnson Space Flight Center for testing in this cryogenic environment. So we loaded the whole thing up in this container and put it on a C5. And then flew it into Ellington Air Force Base and took it out. And then the telescope went into this enormous vacuum chamber. Now, this was made in the Apollo era, and they used it to test like the vacuum characteristics of the lunar landers. Astronauts went in here with spacesuits at some point, you know, but it's just barely fit in there. In fact, a lot of the design decisions in the telescope were made so it would fit in this chamber, so we get it through the door. But this was a test that took place over the summer and into September of 2017. And if any of you think Houston, September 2017, if Hurricane Harvey comes to mind, yes, indeed. I have never seen so much water in my life. It was an exciting experience. If you owned real estate in the area, it was terrifying. Afterwards, you would go around the neighborhoods. Everything looked normal, but pretty soon the road would dip down a little bit and the contents of everyone's house would be in the front yard, just because houses were just destroyed by neighborhoods from this flood. Unbelievable destruction. Here we are. We had the building we were in for testing was fairly old, so we had to build covers to go over all the instrumentation, all the computers. There, I'm the guy in the middle there. There I am riding my bike through Hurricane Harvey. Now people say, how can you ride your bike through hurricane like this? And I say, how could you not? When you gotta get a chance to do this. And keep in mind, someone took that picture too. This is my buddy, Bruce Dean from NASA, and he was running in this stuff. So he went out running and ran 30 miles that day through this kind of flood conditions. So then the telescope, the time came to move it from Northrop Grumman, where it was fully integrated with the spacecraft, to be put onto a boat to be taken to South America. Here it is. This was done under like 2 in the morning. There was no announcements, no press told that this was happening. And they just got it on the regular roads and went because they didn't want people following and everything. And there it is, moving down the highway. That's just regular traffic there with it. And finally put onto this boat, the MN Colibri, and it went down through the Panama Canal and arrived October 12th in French Guiana. There it is in Peru, arriving in French Guiana. Here it is being taken off the boat and being moved into the processing facility. There it is, it's being attached to the docking adapter. That was a bit of a problem with that. There was a bolt broke, but everything was okay. Being prepared for fueling. Now, fueling is not something that's easily done. This fuel is hypergolic fuel. It's extremely toxic. So the spacesuits are not for vacuum. They're there to just protect the people from any potential contamination from these hypergolic fuels. All right. And finally, the telescope was placed on top of the launch vehicle. The launch vehicle is underneath it there. And the fairings were put on, and then the launch vehicle is rolled out to the pad, launch pad. And here we are. There's an earlier version of it, but this is the Ariane 5. At the time, if we had the program today, we probably would use a Falcon Heavy. But you know, at the time, this was the only vehicle envisioned that was capable of putting something this heavy out at L2. All right. Now, earlier I showed that church where we had a conference and everybody was standing outside in front of the model. The European Space Agency wanted to bring a model of the Ariane 5 and show it to everyone. And this is a scale model of it. And the only place it would fit was in the sanctuary. Now, this was an old Catholic church that was converted to a museum, but you know, here it is. And I'm looking at this, and that kind of gave me the creeps. I don't know, you know, a rocket in a church like this. And I couldn't, I just thought about it. I searched my feelings and I realized I remembered because I saw this movie when I was a kid, you know, Beneath the Planet of the Apes with Charlton Heston. And that's what scared me about it. This was a story about some people who lived underground and they were mutated from the radiation and they worshiped this nuclear missile and all that.
That's Omega Man.
No, that's not Omega Man. This is Beneath the Planet of the Apes. All right, so here we are. I think I'll play just a little bit of this. The sound is less than ideal. Let's see if it goes. This was the launch.
T-minus 30 seconds and counting.
Let's skip some.
7, 6, 5, 4, 3, 2, unité, stop. And we have engine start. Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And I have to say, when this occurred,
Through the clouds, 20 seconds into the
I
flight,
felt very,
program reported.
it was like giving your daughter away at a wedding or something, you know. It's just, it was like, yeah, I realize this is what it was made for, but it was, wait, no, you're not supposed to be there in space. You're supposed to be on the ground. You've been there for 20 years, you know. But in any case, the launch went, everything was successful. And back to the bicycling, I went on to Gibraltar. The Royal Air Morocco Airlines would not give me my bicycle, so I spent a week there waiting for them to give me my bicycle. I finally did. I got it, and I took off. And I tell you, that bicycling through Spain was very, very difficult. Very good roads, but they don't allow bicycles on them. And you know, the path I had laid out, it was very, very hard. I ended up punting. I only went about 400 or 500 miles in Spain, and I ended up switching from there. I went to Nantes, France, and biked across France. Beautiful, beautiful place. Ultimate bike paths. I mean, there is a bike path that goes along the Danube River, and it goes forever. It's a couple thousand miles along the Danube River, and it's all path. It's just amazing. What a beautiful experience. Sometimes, you know, it's a little muddy, but that's okay. It makes it interesting. But the architecture. So then in Switzerland, this was a path that I was on, and at the end of that path was a bridge, and at the end of that bridge, stairs. I'm thinking an international bike path with stairs on it. And my bike weighed 100 pounds, so I had to take everything apart to get it up these stairs, but it was okay. There's Lake Geneva. And then I went to the Geneva Observatory, gave a talk there, met some guys. There's astronaut Claude Nicollier, the director. On to into Germany, along the Danube River. Beautiful hops. Boy, I don't know if you like beer, but just the smell of hops, a hops forest. It is unbelievable. It's so beautiful. Just unbelievably beautiful. Into Vienna. Stopped in Vienna and gave a talk here. Anton Zeilinger, he won the Nobel Prize a little bit back in quantum communications, quantum information. Into Bratislava, Slovakia. Beautiful place. And on into Hungary. All right, let's show this video real quickly of how the telescope deploys. Well, right after launch, the very first thing that happened was the solar panels unfolded. That happened very quickly. Good thing, because we can only go a few hours without power. High gain antenna, and then after a few days, the sun shield began to unfold itself. And this was a nervous time because we didn't know if this was going to work. We hoped it would, but it's just a very hard thing to do. So then the tower deployed, moved the telescope away from the spacecraft, and then the unfolding and tensioning of this sun shield. Skip a little bit here. And when they finally were able to confirm that this thing was tensioned, boy, you want to see some sighs of relief. You know, mine was one of them. Because nothing works if this thing doesn't get deployed correctly. Then we have to unfold the wings and the secondary mirror. And now we got a telescope. Okay. So now I'm going to show a movie that shows how we phased the telescope from the beginning to the end. I'm not going to go into the science of this very much, but I want you to see what the people running, operating the wavefront sensor control computers would have seen. And every time you see an image move, it's an image made by one segment. And basically, anytime you see something move, somebody had to look at an image, decide that had to move, figure out how to move that mirror, send commands to the telescope and all that. So this took many, many days. Let's see if we can just play it now. All right, here we go. So we moved all the segments after we found them into a common place in the middle, and then we formed an array so that we could take the telescope out of focus and use something called phase retrieval to work out exactly what we need to do to each mirror to make it individually perfect or pretty close. And after a few iterations, we got that right. And then once this is done, we then need to put all those things so that they fall on top of each other. So this is a multi-step process. It takes a couple of days. And now all the segments are on top of each other, but they're not phased. So see, we have to do something known as dispersed fringe sensing, which is like using a diffraction grating to measure the distance between segments between those segments, and we apply them as corrections. And then we need to go around and measure how the optical aberrations vary as a function of field position. And we do that by moving it around to the corners of one of the NIRCam modules. And this was it's fairly mathematical, but it actually makes it possible to put the secondary mirror in the right place so that it makes a good image not just at one place, but all over the science instruments. And all right, let's get through this. And finally, so then we moved the segments back out into this big array and did one last little tweak to get the aberrations small within each of the segments. And then once everything is good, we had to move it so that the spots would go exactly into the center, and they didn't. There was a screw up. Basically what happened is I went to bed and someone made a mistake, but it's easy to fix. And so now we're using this thing called phase retrieval again, where we look at out of focus images and work out what we have to do to the individual mirror segments to bring them into sharp, crisp focus. And after a few iterations of this, and a few more iterations, the use of the spectrograph, we end up having all the segments phased with respect to each other so that it makes a perfect diffraction limited image. And that took about 4 months. All right, let's I'll skip over this now. All right, so I'll show you some results of that in a second. But after being in Europe, I went back to Boulder and put my bicycle in exactly the same place. And I decided to ride south to Key West, Florida. And I love this part of the ride. I actually got out of shape on this part of the ride. It was so kind to me. It just wasn't difficult at all. And I just love the beautiful scenery, just downtown United States. There's something about that just really appeals to me. There's my buddy Sam Cooke. He's a professional opera singer. But just beautiful. Now the bugs can be a problem. This was in Texas, but the fire ants, when you're camping, can be a real concern. I did okay though. Just stopping and giving talks where I could. There's the mighty Mississippi River into Alabama. I saw this guy. He was pushing this large globe over the earth, and I later decided that he must be a fellow named Mark Baumer who decided to walk across the United States barefoot to raise awareness for climate change. Unfortunately, just a few days after that, he was killed with a car hit him. But places that I'd never been to, the Florida Keys, this bridge across the water goes on and on forever. Just beautiful, beautiful. All right, so here was the very first image that we took with the telescope after aligning the mirrors. We set it up such that nobody would see the first diffraction limited images until everybody got to see it. And what happened was, here it is, here's what came down. This was the first diffraction limited image. And we looked around and just all manner of galaxies in there. In fact, there's 241 galaxies in that very first image that we didn't know were there. And one of them need to have a supernova happening in that moment. It's unbelievable. Let's see, here is a full color image of the very first image. Now this is one that hasn't really been released. But at the time we didn't want to release this because we didn't want to steal the thunder from the early release programs. But here it is. This is a full color image of the very first light image taken with the telescope. Now, how do you celebrate the very first image with this telescope? Well, James Webb was born in 1906. All right. Well, you know what else was born in 1906 was this bottle of cognac. And me and my buddy happened to be co-owners of this cognac. So we got together and we, about 70 of us, had like a little 1 ounce pour each. And we raised a glass and we toasted James Webb and the telescope that bears his name. It was quite a deal. I don't actually drink anymore, but I got a little tipsy on that. And I remember tweeting to a friend that I wished you could see the universe from my perspective. That I said, we are surrounded by, and I'm searching for words that that only come to you when you have the clarity of a little bit of alcohol in your system. And I said, we are surrounded by a symphony of creation. There are galaxies everywhere. And later, that quote it went viral. It was in CNN. It was in Forbes magazine. It just somehow resonated with people. And I didn't have the heart to tell them that I only said it because I was toasted on pre-prohibition alcohol. But anyway, it was quite an experience having that. And there I am holding the bottle. So later we took an engineering image just to basically test how stable the telescope would be. And using the fine guiders, we ended up having this image taken here. And this was a complete accident. And this image contains, believe it or not, 10,000 galaxies. Unbelievable. If you just pick a little section here and zoom in, you see every little dot is a galaxy. Amazing. This changed the way I think about life. I think about universe. Just knowing that these galaxies are just, you hold up, this is like holding up a grain of sand at arm's length. And this image here has 10,000 galaxies. So there are probably 1 trillion galaxies available that we could conceivably image with this telescope. It just blows me away. So we did have a little micrometeor hit one of the segments a while back. This actually happens quite frequently, but this one was a little worse than others, but it's okay, no problem. But this is a picture. You can see the bump that it made in the mirror figure. On to New Zealand. Beautiful, beautiful country. Just wonderful mountainsides, very rugged, very difficult place to bicycle, but the most wonderful people I've ever met in my life are from New Zealand. There it is, Baldwin Street in Dunedin, steepest street in the world. Yeah, indeed. And I woke up one day and this picture was in the newspaper, a whole article about me. You know, some guys just took it and ran with it. You know, I was just blown away by this. Now I want to show some pictures from the telescope, but first of all, I want to show a different telescope. This is Lord Ross. He built the world's largest amateur telescope. A long, long time ago. And to this day, it still has the record for the largest amateur telescope. And he used this telescope to look at nebula, which of course now we know are galaxies. But here's a picture. He looked at this one, for example. This is not his image. Obviously, the cameras didn't exist. But he made a drawing of this. And I think drawing your things you see are so good. And here's one of his drawings. Now, this is a drawing. Just take a look at this and think drawings in the mid to late 1800s. And when I'll ask rhetorically because we're on Zoom here, but if this reminds you of anything, and invariably when I give a talk to adults, they come up blank. But when I talk to kids, I guarantee you some of them will say Starry Night, Vincent van Gogh. And I can't prove this, but they were contemporaries. And I suspect Van Gogh saw some of his drawings and said, that's in the sky. I'm going to paint that then. And that was probably the inspiration for his series of paintings that showed these kind of swirling patterns in the sky. And, you know, we have this, this is bacon. I don't know why I threw that in there. Okay, bacon. But these pictures, they're just beautiful. You know, we have this expression, twinkle, twinkle, little star, how I wonder what you are. You know, we are attracted to the beauty of the universe before we ever ask the scientific questions. So if you have an artistic bent, astronomy is for you. And it's the right response to say, this is a beautiful picture. But if that beauty then asks you to say, why are those galaxies stretched out just like that? I wonder what's going on there. Well, then that's good. But the beauty and the appreciation of that beauty comes before the science. Jupiter, my favorite planet. I'll tell you lots of stories about Jupiter at the Keck Observatory. Here it is. This is some ducks. There's Jupiter again. Saturn. No, I'm sorry, that's not Saturn. That's Neptune. But these pictures, the pinwheel galaxy in different wavelengths, and you see a different object. The ability to go into the infrared has given us another dimension. This is a binary system where one of the stars is in the process of consuming the other, I believe, and you see these rings made that have an 8-year period. So you can actually, count this by counting the rings, just like you would in a tree. Now here's some spectra off of some very, very old galaxies, and this has created somewhat of a mystery. It's why do we see oxygen in neon inside of galaxies that are we believe quite young? And something's not understood there, because in order to have oxygen and neon, you have to have supernovas. And this is very abundant. And so it means that this galaxy, something has caused stellar formation and death to go much faster than we thought it was, or the galaxy is older than we thought, which makes the universe older. So it's a bit of a mystery. I'm sure people will figure it out. And here's just beautiful pictures. This is a mid-infrared imager. I like this because this compares the Webb image with the Certif, the Spitzer telescope of the same part of the sky. You can just see the improvement in the resolution in those mid-infrared wavelengths.
Mm-hmm.
And finally, the last picture is the Tarantula Nebula. This, even with Hubble, this remains my favorite image. Just something about it. So if I were to look at to just summarize the key scientific results after the first year and a half, I guess now, of the scientific operations, the pictures are incredible. You can't beat that. The early universe has larger galaxies and more mature than we were expecting. And plus, you can see organic compounds in the early universe. That's sort of a surprise. Supermassive black holes, galaxy clusters that existed in the early universe. Also, we're seeing organic molecules. I'll leave it at that and not claim that we've found life or anything. And using differential spectroscopy. The coronagraphy works, so we have an instrument that makes the star disappear, so that you can do a better job of seeing companions that are near that star. And for me, I'm just really glad the wavefront sensing control worked, because if it didn't, we would be having a very different conversation right now.
Mm.
All right. So guys, that is all I have to show you today. Appreciate you taking an interest. This is something I'm obviously passionate about. So we have time for questions if you want.
Absolutely.
Thank you, Scott.
Hey, you're welcome.
Feel free to stop sharing your
Okay, let me,
screen, and everybody else unmute as you see fit. Okay. Do we have any questions, Mary Ellen? Oh, unmute. You'll have to unmute.
I was just giving a thumbs up. I thought it was a great presentation. Very
Well,
interesting.
I'm glad you enjoyed it.
Yeah, excellent.
Well,
Paul.
yeah, apparently this telescope has opened up the idea that there's a lot more galaxies out there than we may have thought. Does anybody got a guess what all of it is? I know we can't see the other side of the universe, but you got any idea how many galaxies you think there are overall?
Wow. I was surprised by this. A lot of people were. Some people weren't. And, there were some theoreticians who figured that we ought to be able to see about 1 trillion galaxies, and that's kind of what we're seeing. But there's at least 1 trillion galaxies that are available to us. So because of inflation, we don't know how much, but there's certainly parts of the universe. If there's any inflation, there are parts of the universe that we can never see. And because it's, redshifted past us, we will never be able to have any kind of communication with that part of the universe. And so it depends on what fraction of the universe you think we're seeing, right? If the universe is infinite, then the number of galaxies is infinite. But if it's somewhere between 1 trillion galaxies and an infinite number of galaxies, I'm afraid that's all I could say. I will say this: that was when the way the telescope works, right? The data is managed. You take an image, and that then gets put into a buffer in the memory, and then you take your next image, and then that pushes the buffer image in the buffer out, and it goes into the memory that's downloaded. And so if you're not careful, the very last image in your observing program will be stuck in that buffer. So we always would stick a complete throwaway image at the end of an observing session, so that you make sure, we call it a buffer flush. And early on in the commissioning, the segments were stacked but not phased. We put a 40-second integration on one of the guider instruments, so not even a science instrument. And eventually you get that one too. But when I stretched the contrast in that single image, a 40 seconds integration, there were over 500 galaxies in it. And I knew in that moment that every image was going to be a Hubble ultra deep field. And walking back from the, in the middle of the night, it was I'm talking to my wife. I have to confess, I was in tears. Because I envisioned the galaxies. I didn't hear them, but I imagined that the galaxies were singing, that they were expressing joy, that after all this millennia, humanity could finally see them, And so that's out there. It's just unbelievable what there's there. It just completely changed my whole, well, I say worldview, I mean the universe view. Yeah.
Paul, excuse me, Arthur. I think one possible explanation for the myriad of galaxies, perhaps an excess of galaxies, is that they might have gone through a phase of intense star formation.
Yes.
That's one of the explanations. We have no idea yet. The proper.
Yeah, that would do it. And but but they have to be stars that burn themselves out very quickly, so that you can get a couple generations of stars, in 500 million years. Yeah.
You get born kicking and screaming.
Yeah.
Forgive me if I'm answering or asking something that's been answered already, but are you guys able to get any ideas on the metallicity of those early galaxies?
I don't know. I mean, that's a fair question. I mean, that would obviously give you maybe a different measurement of the age, right? But it still comes down to, is it do you have some other mechanism that is creating that? Is faster growth or development of stars, or is there a period of that this is different than it currently is now? I don't know. Yeah, sorry, it's not a very satisfying answer, but the truth is I'm not an astronomer. I mean, I fake it pretty well, but they're not asking me these science questions, right? I'm the guy who phased the mirrors up so that it worked.
Well, here's a more personal question. Given your expertise in dealing with wavefront sensing and correcting, what happens when you come across a pair of binoculars? Do you apply the same thought processes when you're trying to get the two binoculars co-aligned?
Yes, you do, except here's the wavefront sensors up here, right? If you have you have a separate focus for each half of the binoculars, and that's an actuator. You could think of that. And so in a sense that's a fairly good analogy, except that we have hundreds of knobs to adjust, and it's all in the same image. It's all on top of each other. We have to figure out how to sort it all out. Yep.
It's remarkable. It's amazing that you guys were able to do it.
Yeah. Well, I tell you, it's I'm always the pessimist, and I was given chances of success to be in maybe over 50%. The program manager, Bill Oakes, was on 60 Minutes, and they asked him what he thought the chances were, and he said, "I'm 100% certain it's going to work," and he was right. He was right, because it did. But I just worry there's so many things that could go wrong.
Right.
Every simulation is doomed to succeed, and everything we've done up to this point was with simulations, and it really worked well, though. There's here's an example, and stop me if I'm rambling, but when Neil Armstrong and Buzz Aldrin stepped on the moon, and they walked around and they were jumping up and down, seeing how high they could go, and they were singing songs. You remember that?
Mhm.
The world was watching, and the whole world laughed and sang with them, except for one guy, the guy who invented those spacesuits. He was just about to die. And he just knew they were going to break one of those spacesuits and they were going to die on the moon, and it was going to be his fault. And like I say, I'm moved by the fact that the galaxies are up there singing, but I'm just happy it worked. I am just happy that it didn't fail and it wasn't my fault.
Scott, do you have any idea, did anybody keep track of how many individuals, contractors, etc., worked on this project over its life?
There are estimates, and it's like 30,000 or something. I mean, it's just unbelievable. And it is it's comparable to, I guess the Wall of China was a slightly larger effort. But that's the only individual human endeavor that took more effort. Yep.
Bill Wall has a question.
Yeah, I really enjoyed your presentation. I'm
Thank you.
glad that you had that procedure to fix your coronary arteries, and
Yeah.
that turned out well. This is a very exciting project you've been involved with. What are you going to do in the future? Are you going to be
Yeah, that's a good question.
another space project, or?
That's a very fair question. It has obviously, that's an existential thing that it was on my mind years before we got to completing this. The company I'm still at Ball Aerospace. They have, but I've worked on this project for so long. The company has changed underneath me, and there's not a whole lot going on there. So I've got to figure out what to do. I still am involved in analyzing all the data when it comes down to the wavefront sensing data. And just as a double check to what's happening, there are people that are now employed by the Space Telescope Science Institute that do that on a daily basis. And I'm just kind of a double check. Like when we got hit by that micrometeor, I was involved in had to move the mirror about 1 millimeter to correct that error. Yeah, so it's there is the next biggest telescope, but that's kind of just in the concept phase right now. But there's some work on that, and that will use something known as coronography to basically take spectra off of extrasolar planets that are within, say, 100 light years or something, and so we are actively figuring out how to do that. You could certainly argue that it's impossible, but I suspect we'll figure it out. And I don't know. The world record for the oldest person to cycle around the world is 56. Can you imagine that? I could have done it on a unicycle at 56. So maybe I'll take a whack at the world record for the oldest person to cycle around the world again.
So you're gonna for your next project, you're gonna work on some new telescope, and then you're gonna go around the world again on a bicycle, or go around
maybe
on
I'll
a
do
unicycle, or
I don't know. The way the internet is now, and everybody is not afraid of remote working. I'm talking to you on a Surface Pro laptop, which is extremely lightweight and very, very powerful computer. And maybe I'll just do private consulting here and there while I'm traveling, or maybe I'll just stay here and play with my grandkids. I don't know.
Oh, there you go.
I like your
Thanks.
Spock and Kirk picture in the background.
Oh yeah.
Is that a Geiger counter on the shelf back there?
That's a war meter.
A what meter?
It's the war meters for radiological defense. It's like if back when the Russians were going to bomb us, we got nuclear fallout and stuff. It's designed to detect that kind of stuff.
So like a Geiger counter.
Yeah, same principle, but 1,000 times stronger radiation.
Oh,
Yeah.
that point you'd be dead.
Well, that's the idea.
Wow. Great lecture. Thank you so much. Very entertaining.
Yeah.
Well, I'm glad you liked it.
Yeah. Thank you all. We have recorded it, and I will send out a notice when it's posted to the YouTube channel.
Thanks, Bill.
Okay.
Scott, fabulous job, really, and what a wonderful melding of the space telescope and your own personal journey.
Yeah, it has been a journey, that is for sure.
As always, Excellent.
Good
Thank
luck,
you
good luck on
all.
yours.
Happy holidays to everyone.
Have a
You
good
too.
New Year's.
Bye-bye.
Thank you, Scott. Thank you.
Happy New Year.
Enjoy it.
You're
Merry
welcome.
Christmas.
Merry
Oh, happy
Christmas, Happy
holidays.
New Year. Yeah, Merry.
Bye.